Hi folks, and welcome back to Open Analysis Live for part 2 of our Bokbot IcedID analysis. So where we left off in part 1 was we had unpacked the custom Bokbot injector or loader, and we'd opened it up in IDA. So if I just pop over to my VM here, this is where we left off in part 1. Now, one thing I've done that's a little bit different from where we left off in part 1 is I did a second dump of this process just after we unpacked UPX, and I let this first function run, and then I did the import address table rebuilding after that. And the reason for this is if we jump into this function, jump into the first one here, we can see there is a call to read fs at 0x30, which is the process execution block, the PEB. And it looks like they do the walk to basically build some imports. And if we pop back here, that's what they're doing over in this function here. And you can see here, they are basically walking through the PE file and building up some imports based on some data in here. So what I did was I let this function run here, and once it had returned, and I built the imports after that. And so what that allowed me to do was that allowed me to annotate some of the imports that are being dynamically built in this PE file. So that's kind of a cool trick if you guys are lazy and you don't want to go through labeling the imports yourself, and there's some dynamic imports. What you can do is actually just do a silo dump after the import table has been built, and then do the import dump after that. And so that's given us some extra imports, and that's why this looks a little bit different. But that's the only thing that I did that was different from when we left off in part 1. So we know that this was the import address table builder, and I think they were decrypting some strings in there as well. I can't recall, but it's not particularly important for the injection that we're going to be doing, so we can kind of ignore that. The next function that we have down here is this one, and so what are they doing here? It looks like they are grabbing some versions of Windows, trying to figure out what version it is, trying to get the permission level that the process is running at, and if this fails some checks, they call into this function, which does some stuff and then exits. So it looks like they're trying to do a run as, which you can use to elevate permissions of a process. So and they're grabbing their own file module name and they're passing it to shell execute. So it looks like they're just trying to run themselves with higher permissions if they don't have the permissions that they need, and then they exit. So this is not too important either. So that could be one way to try and elevate privileges if they can. But again, not particularly interesting for us. So it's not particularly interesting for the injection technique that we want to analyze here. So if we come down, let's take a look at these guys. What are they doing? Looks like maybe they're getting a length of buffer or something. I'm not really sure, not important. And then the next function we have is this one down here. Now what's kind of interesting is they're actually passing the address of NT create user process into this function. And anytime you see something like that where they pass the address of an API call into a function, personally I always think about hooking, because why else would you need the address of an API? It doesn't make any sense, right? You can always just look up the API in your import address table if you need to use it. Why would you pass the address in? So usually when you see something like that, it tips you off that there's going to be some hooking involved. They pass a pointer to a function and then some data, I guess. So again, this, to me at least, this looks suspiciously like they're trying to set a hook here. When you pass the address of an API and the address of one of your own functions to a function, 9 times out of 10, it's probably hooking. Let's take a look at what they're doing in here. We'll rename this as, so I'm just pressing the N key to rename variable. So rename this as arg, and we're going to name this as arg function address. So let's see what they're doing here. So they assign the API address to A3, and okay, here we go. Yep. So here they are writing the byte E9 to that address, which is the API address, and E9 is the opcode for jump. So I just know that because, read a lot of assembly, but if you didn't know that, you could look that up in the opcode table, and you'd see that that's jump. And then what do? They write just after the jump, so +1 byte, they write the address of the function. So it looks like they're writing a jump to their function to the beginning of that API. And what was that API again? That was NT-create-user-process. So from reading these blogs about Bokbot, I know that they set a hook on their own NT-create-user-process. So this looks like where they're setting the hook. So let's name this set hook. And that would mean that this function here is the hook code. So let's just grab this here, and we're gonna name this hook NT user process. And if we pop into the hook, if you're curious what these functions do, yeah, they're just changing the protections on the memory so they can actually write the hook into that API. So nothing really fancy there. Let's take a look at the hook code because that's probably important. So what are they doing here? They are, okay, so it looks like they are actually calling NT-create-user-process from inside here. So perhaps they remove the hook somewhere around here. Yes, I believe they do. So what they've done is they take away the hook so that they can actually call NT-user-create-process once they're inside their hook code. So then they actually call NT-create-user-process. And for those of you who aren't familiar, NT calls are the calls in ntdll.dll, and they are the lowest level calls in user space, and they also exist in kernel space. And what they are they're the call into the kernel for these APIs from user space. So this is the lowest level you can get for creating a process. And in some of our other tutorials, we talk about hooking create process internal W, which is the lowest level userland call to create a process. However, that's not entirely true because create process internal W in fact calls lower into these NT calls, and it calls two NT calls that are important for what we're doing here. It calls NT create user process, which actually creates the context for a process. Then the actual process data is written into it, and then NT resume thread is called on the main thread for that process. So this is actually how a process is created normally in Windows. And what they're doing here is they're actually hooking that NT create user process call. Then they actually create the process, and then they're going to do some stuff down here, it looks like. So this is kind of interesting. You might be wondering, like, why would you do this, basically? And I suspect what they're trying to do is they're trying to avoid sandboxing or antivirus detection that looks for processes being created suspended. So in this case, by hooking this API call, they don't have to actually create a suspended process. All they need to do is just use these NT create user process and NT resume thread as they would normally appear in Windows operation. So there's nothing anomalous about, is that a right word? There's nothing anomalous about seeing NT create user process and then NT resume thread, because again, that's the normal process that happens when a new process is created. So I suspect that probably in here somewhere, they're going to write some code into that created process. And again, I had a heads up because I read the blog post on how this injection technique works, but let's go through it anyway. So what we see here is we see function call here, RTL decompress buffer, which is just used to decompress a buffer, just using a compression algorithm. So the decompress buffer will be stored into this variable here. And I know this because I just know the arguments for RTL decompress buffer. And we in fact have another tutorial video, which I'll link below, where we describe a technique for hooking RTL decompress buffer to identify interesting code. Because a lot of the time when you see a packed sample, they'll use RTL decompress buffer to actually decompress the code. And I suspect that's what's happening here. So a quick trick is to put a breakpoint on RTL decompress buffer and take a look at what's coming back in those buffers. Sometimes if you're dealing with packers, that's a good way to kind of quickly unpack them. In this case, they're grabbing that buffer that's decompressed and they're sending it to this function here. What is A2? So A2 is the handle to the newly created process. So here we can see NT create user process. The first argument is going to be the handle to that process. So they pass the handle to that process. They pass the, I'm going to rename this as var decompressed buffer. So they pass the decompressed buffer and the length of the buffer. So I strongly suspect they're going to be writing some stuff to this process. So let's take a look here. That's the process handle. We're going to rename this as arg buffer. And again, that's where we pass in our decompressed buffer. So let's see what they do with it. They grab everything except for the first D word, put it into v19, not particularly interesting for us. Here they pass, here we go. So we see a process handle, the buffer, the length of the buffer passed this function. And I suspect one of these is going to be allocate virtual memory. So they're going to allocate some space into that newly created process. And I bet this is a write here. And they're going to write to that process. Okay, so here's what we've seen so far. I know this is kind of fast, but I'm actually going to go through this live in a debugger afterwards. So this is just to show you how you would statically analyze this. And we'll go through it live in a debugger and you'll see how all this works. So what they've done is they have hooked create user process. Once they jump into this hook code, they remove the hook, use create user process to actually create a process. Then they decompress a buffer that's stored in the PE file, and then they write that buffer into the process. So now that we've kind of figured that out, let's see what else they're doing in this function here. So this was where they were writing it in, I believe. So let's just rename this name allocate. And let's pop back here. This is name wrap write memory. And this is buffer write buffer to process. All right. Okay, so we've covered that off. Now what else are they doing here? They're grabbing their own module name. They're going to store the address of RTL exit user process. This is interesting from the blog post as well. They talked about how one of the things that they do is they will hook RTL exit user process of the process that they're injecting into. And then in that hook, they will have a jump into the code that they injected. So perhaps that's what we're seeing here. We see this function call. We see the address of RTL exit user process being passed. And we see this right here, which is get module file name, which is part of our file name. I'm not too sure what they'd be doing there, but let's take a look. No, they're not doing anything interesting here. They're just copying some stuff over. So let's see where else they use this RTL exit user process. Okay, so they're also passing it to a function down here. What else are they passing into this function? Process handle of the remote process that they created. Okay, here we go. Now we're getting somewhere. And they pass in v17. Let's see what they have here. A bunch of dereference pointers that I'm too lazy to go into. So let's just take a look here and have the process handle. We have the address of RTL exit user process. And again, here's our old friend where we're passing in the process handle, the base address, and a bunch of other bytes. Okay, here we go. I see what's going on here. So they must be finding the offset to the injected code, and then they're going to write that into RTL exit user process, and they're going to write a jump to that injected code here. So it looks like this is where they're setting the hook into RTL exit user process. And again, I'll go through this live in a debugger so you guys can see exactly what's going on. And in the blog, they explain why you would do this, and it makes perfect sense. So what they're doing is they're starting svchost.exe. So in part one, I explained how they have a stack string for svchost, and that's where they're creating the process. And if you start svchost with no arguments, it'll just immediately exit. So what they've done is they've hooked the exit call and they've added their own code in there. And so what this does is it's very clever. When svchost goes to terminate, instead of terminating, it'll actually run the injected code. So that's what they're doing here with this little blob. And they're actually hooking their own function in order to do that, in order to make the API calls that they use blend in with normal operation. So very cool, very interesting way of injecting code. And one of the things about this that is going to be interesting for us is when you do something like this, you're not going to be injecting a PE file. You're going to be injecting a bunch of position independent code, or code that maybe does rely on position, but has been relocated for the address that it's injected into. So I think this is one of the first tutorials that we've done where we won't be dumping out a PE file. We'll be dumping out a bunch of code, and we'll have to make sense of that. So that's what makes this a little bit more interesting and a little bit more advanced. That, and also this kind of cool injection technique. So if we pop back to main function here, and we can see that after they set that hook, here is the stack string that has SVC host, and we can see it's being built into it. So they actually call create process A with svc host.exe, and that's going to trigger this hook that they just set. So that kind of completes this kind of interesting injection technique. And what we're going to do now is we're going to pop over to our debugger VM. We're going to set some breakpoints on NT create user process, on create process A, and on NT resume thread. And we're going to see if we can't see this injection in real time. And then we will take a look at svc host, and we'll set a breakpoint on RTL exit user process, and we will see if we can't see that hook being triggered and locate the code that's been injected. And at that point, I'll show you guys a trick for analyzing injected code. That's kind of cool. So without further ado, let's pop over to our VM and get her done. Okay, so we are in our debugger VM here. We're going to open up x64 debug, and we're going to open the IcedID custom injector or custom loader in x64 debug here. So just like I showed you in IDA, what we want to do is we want to set some breakpoints on these interesting APIs. So I'm going to set a breakpoint, just use the BP command here on create process A, because that's where they create the SVC host. So that's the top level call. Now, not particularly interesting for us. I just want to show you that after that call, we're going to jump into the hook code. So what we want to do is we also want to set a breakpoint on NT create user process and on NT resume thread, because of course we want to see when they resume that process. We want to stop before they resume the process. So let's do a breakpoint on NT resume thread. Okay, so if we look at our breakpoints here, we now have one on create process A, on ZW create user process, and NT resume thread. Now, you might be wondering, what's the difference between ZW and NT? And in user land, it doesn't really matter. You can think of them as the same API calls, even though they have a different prepended 2 bytes. So ZW and NT in user land, you can think of it as the same thing. In kernel space, it's different. Just to explain it, what it means is if you're calling ZW APIs, the kernel assumes that you know what you're doing, and it doesn't do any extra validation on the arguments that are passed. And if you call NT, then it does extra validation. Both the APIs are accessible from userland, but of course, anything from userland, it's just going to treat as untrusted, so it's going to do the extra validation on the arguments anyway. So both those APIs are essentially the same from userland. So let's pop back to our assembly view, and we'll just run here. So we jump to the entry point, because there's always a breakpoint on the entry point, and then we jump to the first API that we hit here, is create process A, and the arguments that we're passing are svc host.exe, just as we expected. So now let's see if we hit the breakpoint that we put on ZW create user process. And here's something interesting. You notice this code here? That's actually a jump to a section in our own PE file. So it looks like this hook has already been set for ZW create user process. So we double click on it here, we can see that indeed there is a jump to this code here. And if we press enter, we can follow it. And let's just toggle an extra breakpoint here just in case. So this is the hook code that they've set on their own ZW create user process. So if we run now, we should see we hit this breakpoint and we've jumped into the hook code. And here's where we see them actually set up the arguments for the real call to ZW create user process and all the other stuff. Here's the RTL decompress buffer, everything else that we showed you in IDA. So now instead of trying to look at all the different writes where they write stuff into the created process, let's just skip all that and we'll break on resume thread. And because we know that they write a hook to RTL exit user process, we know exactly where to look in the SVC host process once we hit resume thread. So we don't have to worry about tracking all those writes to the process or anything like that, because we know exactly where the entry point is going to be. The entry point is going to be in that jump that they inject into RTL exit user process. So let's run till we hit resume here. Oh, our breakpoint on ZW create process was hit a second time, because remember they actually call it after they jump to their hook code. So we're going to continue running here. So now we hit one on NT resume thread. So what we can do is we can open another copy of x64 debug, then go to file, attach, and we see SVC host sitting here in the process tree. So we'll attach. Now that we've attached to it, we're going to want to find RTL exit user process because we know that's where they inject code into SVC host. And we're going to want to put a breakpoint on there so that when it resumes, we hit that breakpoint and we can see where the injected code is. So let's Control G, RTL exit user process. Okay, and we can already see that they've injected this jump to the code section here. So we can right click, toggle a breakpoint on that, and we may as well jump into that function as well, and we'll add a breakpoint here as well. It might complain, it doesn't like to set them in memory, but it's okay. Well, it shouldn't crash. So let's pop back to our other instance where we're debugging here. We'll just let this run out, and it exits out because that's the last thing it wants to do is just resume the remote process. So we'll exit this, and now we're going to resume the SVC host process, and we hit our breakpoint just as we expected. Okay, so now we can jump into this injected code. We'll follow this jump. And this is the entry point for the injected code. So we're going to want to remember that address, C70C8. So we're just going to want to remember that for later on. That's going to be the OEP for the injected code. And what I want to do now is I want to take a little bit of a look at what this code is doing here. So the first thing that sort of pops out to me is we see this like push FFF. Well, we see a call here, but right below it, we see a push FFF. And then we see a call to a pointer in memory, but the pointer in memory is not annotated. So this to me seems kind of strange. Usually when you see something like this, if we actually follow this in our dump here, follow in dump, we can see that it's empty. There's nothing in that pointer in memory. So when you see a call to a null address in injected code, usually what that means is this is where they're going to write the imports. So it means that they're going to dynamically resolve some APIs, and this is probably where they're going to write the import table to these addresses here. So that's why it's 0 now. And then once they resolve it, these are going to contain pointers to the API calls. So what I like to do, this is kind of lazy and a little bit dangerous, but what I like to do is I like to run the code until I see these being populated, because then I know that the imports have been resolved. And then I know that when I dump the code out, the dump code is going to have references to these APIs so that I can label them easily in IDA. Now, in order to do this, it means that you're actually going to be running the code. Now, I'm in a VM with a snapshot, so I don't really care. It's not dangerous for me. And this is going to speed things up a lot. Now, a more careful way to do this would be to actually identify where the dynamic import resolve function is and sort of walk through that and manually label all of the imports. But this is a quick trick. It's very fast and it's safe if you're doing it in a VM. So what I'm going to do is I'm going to actually jump over this call here, and I can see that now all of these have been labeled. So I can see addresses in here, and x64 debug has helpfully added the labels of the APIs into the code here. So I know that now when I dump this code, it's going to have all these pointers in it, and then all I have to do is identify where these pointers point, so which APIs they point to. And I'll show you a pretty cool tool for doing this in a minute. So what I want to do now, before I dump it, is I want to take a quick look at what this code is actually doing just before I dump it, in case there's references to other sections. And I'll show you that there is. That's why I'm doing this. And this is kind of tricky. This might trip you up if you're not familiar with debugging injected code. So if we press enter here, we jump into the code, and we can see there are references to data blocks here, and they are not populated with labels. So these are pointers to addresses in memory. And if we were to say follow one of these in memory, so we follow in dump, we can see that there is an address here. And if we sort of right click and follow dword in disassembler, we can see that we actually pop into another section, the B and 40 section. And we can see that here there are also some imports that have been resolved. So there's some addresses here to a bunch of different imports. So this is something that I saw kind of quickly in IDA, which is why I suspected that there would be references to another section. When they inject the code, they also inject a struct with a bunch of data in it. And I think that this section contains that struct. So what this means is when we dump out our code, we're going to want to dump out the code section and this additional section, which is that B. Actually, let's just follow it in memory map. B and 4 zeros. So it's right below the code section that we want to dump out. So we're going to need to dump both those sections out and load them both into IDA, because of course there's references between them. So I'm going to show you how to do that now. So first thing I want to do is let's dump out this extra section here. We'll dump it to desktop, save. And then we want to dump out if we go back, we want to dump out the code section, and remember the entry point here is at C70C8, and I'm going to actually write that in the file name as well so that we remember that's where the entry point is for that code. So let's right click, follow in memory map, Okay, so right click, dump to the desktop, and I'm going to append to the file name here the entry point, which is C70C8, saved to the desktop. Okay, so now that I have those both saved to the desktop, I'm going to copy them over to our VM that we have IDA in, and I'm going to show you how to load both those sections into IDA so that they reference each other and how to label the APIs for them. Okay, so we have IDA open here, and I've copied the 2 dumps over to the desktop of our VM here. So I'm going to go File, Open, and I'm going to open up the B section first. And so now we have to make some adjustments to how we load it. So the first thing we want to do is we want to disable auto analysis. So when you load up a file, IDA will automatically try to analyze it. It'll try to find all the functions and code blocks and analyze it as code. The problem is that we are looking at injected code. So there's going to be a mix of data and code. And what we need to do is we need to actually show IDA where the code is first and then allow the auto analysis to run after we've kind of labeled it up a little bit. Otherwise, IDA can make some crazy mistakes and it ends up putting a whole bunch of extra information in the IDB that you don't need. So then the other thing that we want to do is we want to change the loading segment loading offset to match the address in memory where we dump the file from. And the reason for this is because if there's any references to that memory section in the code that we dumped, it's going to need to be at the right offset in order to match up in the IDB. So it's kind of like if you think about rebasing PE files, we talked about that in some of our tutorials. This is the same idea where the code blob has to be loaded at the same address where it was dumped from memory. So that's going to be at B and 4 zeros and 0xB. Okay, so we're going to load that up. Yes, we want to analyze that as 32-bit code. Okay, so IDA's loaded up. You'll notice that there's no code identified here because it didn't auto-analyze just like we told it. And now what we want to do is we want to add the other section into the same IDB here so that they can reference each other. Now the way to do that is you go to File, Load File, Additional Binary File, and then we load up the C and 4 zeros section. And here we want to do the same thing. We want to change the load segment and load offset to be the same as the memory address where it was dumped. So that's 0xC1234 and 0xC1234. Okay, so now it's loaded up. Both the sections are loaded. Nothing's been analyzed yet. Now here's a trick. We could go to that entry point. So if we go to our entry point that we put in the file name. So I go to our desktop here. What was the file name? It was C70C8 is the entry point. So we could go to C70C8. And we can see that there's some code here that matches up with what we saw in the dump. And we could press C and analyze the code. But what I want to do is I want to actually add the API labels first, and then I want to run the auto analysis. And the reason for this is because IDA will actually take those labels if you've already added it to your dump, and it will apply it in the auto analysis instead of you having to manually click and define each function call as a label. So it's just a quick trick. It works both ways. If you apply the labels after you've already analyzed the code, it just means that you have to do some manual clicky on the API calls to rename them as the label. This way it's just a little bit better because IDA will do it for you. So there's lots of different ways that you might want to label the APIs. There's tons of different tools. The tool that I like to use is called API Scout from Daniel Plowman, PNX, as you guys might know him. He runs the Malpedia project and has a ton of awesome tools. So I'll actually link to his GitHub below with IDA Scout. And the way it works is you actually build a list of APIs and DLLs and their offsets in memory on your debugger VM. And then you actually copy that list over into your IDA instance and then run his tool, and it will identify all of those offset values and then apply labels to them. So I'll show you how this works. So we pop over to our debugger VM here, and I have API Scout sitting here on the desktop. So it's a Python project. And what we want to do is we want to actually build a database. So I'll run it from the command line. Okay, cd into API Scout and cd into DB builder, and what's it called here? I think it's called database builder here. So we're going to run Python database builder -- let's see what the help commands are for it. Auto is what we want. So we're just going to do -- auto. Okay, so this takes a while. So I think through the magic of Cinema, I'm going to skip over this. But what it's doing now is it's enumerating all the DLLs on this host, and it's building an offset map between the API address and the API name. So let's skip over this building. Okay, so now that that's complete, the database is going to be written to the same directory where we ran it. So API Scout DB Builder, and it's called filter.json. We could have just called it anything we want. There's a command line flag for that. But now that it's saved out as this JSON database, we want to actually copy this over into our IDA VM, and we want to run the IDA Scout tool here with that database. So let's pop over to our IDA VM, and I'll run the tool, and hopefully we get some populated API addresses. So we're going to run this tool, go to script file, and it's in our shared drive here, IDA Scout, open it up, and there's our database. We're going to run, and here's our results. So it actually worked. Here's our offset in IDA, and here's the label that they've assigned to it. So in order to actually apply this to IDA, you can actually select what you want to be applied in case there's false positives. I like to just label it all, and if there's any false positives, I'll deal with it later. So just right click, select the whole thing here, and annotate. Now that's applied all these labels. So now what we can do is we can actually turn this into code here. So we're gonna press C to turn it into code, and then we can go to our options and choose general analysis and enable our auto analysis. And so now this should go through, analyze all of the code, and add the API labels correctly. So it's running, and you can already see that it looks like it's doing the right thing here. The labels have been applied, but IDA has been kind of stingy with applying the labels to the code, which is what I'd hope to avoid by having it analyze after we applied the labels. It didn't work, I'm not quite sure why, but we can just sort of right click here, and you can see you can choose it, choose to apply the label. And the other thing I wanted to point out is now that we have these labeled, we can sort of right click, change them into pointers. And I think there's another one in here we probably want to take a look at, change that into a pointer. And if we look at this, this is a pointer to the section that we added. So we can just right click, turn that into a pointer. And if we jump into here, we can see that there's a bunch of APIs here. Just like we saw in the debugger, there is this looks like a struct with a bunch of APIs that are defined in this other code section as well. So if we sort of turn these into D words, so this looks like maybe a struct that has a bunch of data in it, and we can sort of start defining it. Now here is where IDA's gone a little off the rails trying to define this stuff as code. Definitely want to undefine that. And it looks like this is a string or something. Undefine this as well. So this is what I was hoping to avoid by not allowing the auto analysis to run, but unfortunately it looks like we didn't avoid that. So we're gonna have to do a little cleanup here. Not a big deal though. This is a string, so let's actually change this over to options. We'll change the ASCII string style into Unicode, and let's define this here with the A key, and it looks like that's a string here as well. Let's sort of undefine this. It's just a whole bunch of null bytes. Looks like there's some URLs in here, so let's change this back into C style from Unicode, and we'll define those as well. And what else do we have here? Let's turn this into a big null byte array. Turn that into an array. Okay, and then down here we have another D word, it looks like, and then some more APIs. And there's another big buffer of null bytes here. I like to clean this up as well, define this as an array, and I'll go edit array. Okay, so now everything's kind of compressed up and easy to see. And what I'd like to do now is I'd like to define this whole thing as a struct. And then you'll see what this does is this allows us to reference this as a structure in our code. So we can sort of select all of these bytes here, and we want to go to edit, struct, create struct from selection. And this is a cool thing. When we create this struct, we'll just name it inject data. IDA will actually add the labels here for you so that then when you reference this structure, you'll be able to see the labels, which is super helpful. So now if we go back here, we look at where the struct is referenced and name it as injected data. And I'm going to look at where it's referenced with xrefs and where is this referenced. And so now anywhere where this is dereferenced, it'll dereference the struct. Now we can't really see this in the assembly view. We have to go into the hexphrase view in order to see this. So why don't we pop over there in a second here. So just F5, and we can see now that the struct is now defined properly, and we can see that the APIs in the struct are now referenced. And so this code is now ready to be analyzed normally in IDA, and you don't need to do any more debugging. You can actually statically analyze the rest of it. And if you have situations like this, where the memory reference isn't picked up by hex arrays, you can always pop over to the code here. So Control C, go to this GV and the disassembler view, and just right click and fix these references here. You can see all these references. They haven't been fixed properly by IDA. It should have automatically done this, but I don't know why it didn't. We basically need to go through and fix these up so that the hex arrays view knows what's going on. And so once we fix these up, I don't see any other one. Oh, there's a few more in here. There should be a way to automatically do this. If you guys know, just leave it in the comments below. I'm not quite sure. The trick that I thought I was describing, where you actually set the labels before you do the analysis, was how I thought it worked, but maybe that was just kind of a fluke. I'm not sure why it didn't work this time. But there we go. So once we have this, we can just press F5 here. 5 again, and it'll actually populate all of these with the correct API names, and the injected struct will be populated as well. So you might have to do that manually for a little bit of this stuff, but at least the data is there and you'll have all the references that you need. So this is how you would go about analyzing IcedID.
Hell yeah! Hell yeah! Hell yeah! Hell yeah! Hell yeah!
And also, this is a great reference for any injected code that's not a PE file. So this is what you would need to do. And just to review the steps here, so you identify where the code is injected in the process. You identify the entry point into the code. So you need to know that to know where the code actually starts. And then you let it run until the import address table has been populated with all the addresses to the APIs. Then you dump the code and you run API Scout to add labels to all of those populated API addresses. And you can also take a look and see if there are other injected sections that are referenced by your section. And if there are, you can dump them out and add them to your IDB with the load file command, just like I showed you here. So a little bit more in depth than a normal dump with a PE and open an IDA, but it's pretty simple once you get the hang of it, and it should work for any injected code. It should be the same process. So now you have the tools to do that. I'm not going to go through the actual analysis of IcedID. I'll leave that up to you guys to do. What I will do is I will include links to the extracted first and second stage in the description of the video below, so that you guys can go through and replicate this yourself. I won't link to copies of these dump memory sections. It'll be up to you guys to actually dump these sections out and build them up in IDA yourself using the techniques I showed you here. I'll also link to Daniel's API Scout GitHub repo. The tool works all the time. It's super easy to use, and I can't recommend it enough. It's probably one of my favorite tools for injected code analysis. So I'll link to that as well. So with that wraps up probably one of our longest tutorials we've done here. Hopefully it stayed interesting to the end, and hopefully there's some useful tips in here that you guys can use. Again, if anyone has any suggestions about how to get IDA to reanalyze after you've applied the labels and automatically apply them, leave them in the comments below. I'm super interested to know. Usually I kind of muck around with reloading the IDB and stuff, trying to see if it'll do it, and usually I can get it to do it. But if somebody could leave a comment about if there's like a button to press or like a function to run that'll actually do it automatically, that would be fantastic. So with that, if you guys have any comments or questions about what we did here, leave them in the comment section below and we'll respond to you. You can always hit us up on Twitter or email. Both those are linked as well in the description of the video below. And also, we're looking for suggestions for things to cover. So if you have suggestions for other malware families that we should cover that have interesting techniques or other tools, definitely interested in that as well. So with that, until our next video, keep exposing the mechanics behind the malware and stay curious.